talk about a different part of the tracing spectrum. I spent years working in computer architecture and then in performance analysis at digital equipment at Adobe Systems, 12 years at Google. I retired from Google a year and a half ago and been teaching a bit half a year as part of my retirement. So I'm interested in observing what's really going on in data center software, which tends to be quite different from desktop or benchmark software. So I'm going to talk about the observability problem, tracing design goals, give a little display of some of the output and comparisons to other tracing tools and conclusions. So the observability problem for data center stuff, this is about not batch processing. This is live load, user-facing load. Users are waiting on their cell phones. They want something to happen on their phone in 200, 250 milliseconds. And there are tens of thousands of such users touching any machine at any given second. And within a data center, there may be 20,000 different servers running lots of different software services. So it's not like, here's the Gmail servers and here's the search servers. They're all running everything. And in that environment, you get hundreds or thousands of transactions per second, and you get some transactions that are slow. You know, instead of taking 200 milliseconds, they'll take 2,000. Or instead of taking 4 milliseconds, they'll take 40. And the interesting ones, the ones I worked on, are the ones that if you run them again, they're fast. So you can't find them except in live load, usually during the busiest hour of the day. And what we like to do is we will observe anything that's unpredictable or unreproducible means that the slowness you're looking for is a function of interference from something else. And the mystery is you don't know the something else. And programmers are inept at guessing what the something else is. That's been my experience. And so we like to observe where all the time goes in one of these servers doing transactions so that over the course of a couple of minutes, you can see in detail what happened. And usually then it's like a 20-minute fix. So there's some source of interference that we like to find. And to find the interference, you can't do sampling, you can't look at user mode only, whatever. You have to see everything that's going on in order to find the missing interference. So I became early on interested in complete traces of exactly what the CPUs are doing on live load. And that the problem is all the existing tools at the time had much too high overhead. So I decided to look at all the transitions between user mode and kernel mode. Every system call, system return, every interrupt return, every fault return, every context switch. If you can see all the transitions, then for any given CPU core, you can say, here's exactly what it was doing every nanosecond. And you can do that for all the cores in a multi-core server, and you can do that across multiple servers and then timeline the traces in order to see this client made this call, and it took an extra 40 milliseconds to get there, and that's the problem. And then you get to figure out which machine was slow, or which network switch was slow. So this is for tracing all executables unmodified. And I found that just the transitions in kernel and user mode have enough information to be useful, and not so much information that it's slow. So this is a one-trick pony. It only does one thing. There will be copies of the slides available. You don't really need to take lots of pictures. So this tool, it doesn't help with fine-grained user mode per routine debugging, as we've seen earlier. It doesn't help with kernel mode debugging. It doesn't have an interpretive language. It doesn't have any subsetting. It doesn't actually have any options. You turn it on. It captures everything that happens for a minute or two and turn it off. So in the context, we have these transactions that take a millisecond to a second, and I'm particularly interested in 99th percentile slow ones. So there's 99 fast ones and there's one slow one. There's 99 fast ones, there's one slow one. in many software development environments, there are people who are really good at the 99 fast ones. They're really good at making the average performance wonderful. They understand lots of algorithms. And then there are these outliers, except that when you're doing 10,000 transactions a second, there's, the 99th percentile outlier happens 100 times a second. So things that you think of as second order effects are happening all the time. And unfortunately, in a data center environment where you're doing lots of work in parallel, like a web search that fans out to 100 machines, which in turn fan out to 20 more machines, and you have 2,000 machines doing a little piece of research, and then you roll up the results, and then you return that to a user in 200 milliseconds. The slowest of those 2,000 machines is the time the user sees. So if you do 100 to 1 fan out in order to get lots of parallelism, you're always running at the 99th percentile slow response. It's a disproportionate piece of leverage. So we care about the slow ones, we care about the surrounding context. And as I said, I usually find that it takes like 20 minutes to fix bugs that have taken months to find. And in some cases, bugs that have been there for 3 years and nobody knew how to find them. So the design goals for this level of tracing are pretty straightforward. Record every transition between user and kernel mode with less than 1% CPU overhead. When I worked at Google and I went to the people who ran the data centers and I said, I have this great tool I need to use to observe what's going on, and it makes everything 10% slower. It's a very short conversation. If I say it makes everything 1% slower, they say, oh sure, no problem. Any number between 1 and 10 is a very long conversation, and usually the answer is no. So for instance, TCP dump is useless in this environment because it has 7% overhead. You could use TCP dump under light load midnight on Saturday, but you can't use it during heavy load Tuesday morning. It slows everything down too much. So 1% CPU overhead, 1% memory overhead, for a window of 30 to 120 seconds. Less than 30 seconds, it makes it really tough to trace on multiple machines and line them up in time and see both pieces of some client-server transaction. And my experience has been more than about 2 minutes, you don't learn anything new. So my design goal is 30 to 120 seconds of trace. Okay, oh, and that means 200,000 transitions per second per CPU core. So if there's 24 CPU cores, that's 5 million transitions per second to get recorded. So the mechanism is something I think we've all in this room seen by now. Some patches to the Linux kernel, a loadable module that has the actual tracing code. Tracing goes into a RAM buffer that's reserved at the time you load the module in kernel RAM, and then post-processing to figure out what actually happened. And the design is driven entirely by the performance goal of the tracing mechanism. So less than 1% overhead for 200,000 transitions per second means there's a transition every 5 nanoseconds per core. So per core, my budget is 50 nanoseconds to record what happened. That's about the length of a cache miss in main memory. So simply from the performance goal, I can't write 64 bytes of data for every trace entry. It's too big. I have to have less than 1 cache miss per trace entry. In fact, the only reasonable design points are 4, 8, or 16 bytes per trace entry. So things that have trace editors and stuff, and you have they're always running process ID number and a CPU number and format description numbers and stuff. It gets way too big real fast. So as I said, this is a different end of the design spectrum. I also want to take less than 1% memory. So if you've got 256 gigabyte of RAM, which is pretty normal these days in data centers, you've got 2.5 gigabytes that you could set aside for trace buffer, 1%. And if you have 2.5 gigabytes and you've got 24 cores and 200,000 transitions per second, you want to record for 60 seconds, you can't have entries bigger than 9 bytes long without using up more RAM than we budgeted. So I picked 4 bytes. 4 bytes is enough room to have the timestamp and an event number. The event numbers are this particular system call, this return from that particular system call. This particular, in the case of Linux for x86, 32-bit system call and returns, which have slightly different numbering schemes and slightly different arguments in some cases. And then there's a dozen different kinds of interrupts you can get and things like that. So 12 bits is enough for the event number. 20 bits is enough for a timestamp. We just use a cycle counter. We shifted over 6 bits to get order of 20 nanosecond resolution on an order of 3 gigahertz machine. That means that 20 bits maps 1,000,000 times 20 nanoseconds or every 20 milliseconds. Now, as long as you have a trace entry per CPU core per 20 milliseconds, you can reconstruct all the high bits of the timer later in software. So we run with directing the timer IRQ to every processor. This means that the Linux no time stuff or no hertz stuff is not compatible with this because you can end up with a CPU core that doesn't take any transitions for well over 20 milliseconds. So I just built the kernel with 4 millisecond timer interrupts, which turned out to be incredibly useful for aligning what's going on in different cores. So it turns out the first version of this I built at Google in 2006 with Prosper Row. Some of you may know some of the older people for doing a bunch of the networking code in early Linux. Anyway, he observed that it'd be really useful to have the value of the first argument to system calls. For a lot of system calls, that's the argument that says which file ID I'm touching. For others, it's what operation I'm doing. And with a little work, we in the early version, squeezed in 16 bits for that. It's also really useful for system calls to have a bit of the return value, because all of the standard error codes are from -125 to -1 tell you about things that often are related to why something is slow. And so having those return codes turns out to be incredibly valuable. So in fact, for the system calls, we pack call and return pair into 8 bytes. So 4 bytes of the call, 4 bytes of the return, but reformat it a little bit. So that there's a single timestamp and the call event. And then a delta time squeezed into 8 bits for how long we spent in the system call routine. Or in fact, we use the same format for interrupts and page faults and things. 8 bits for the return value and 16 bits for the low bits of R0. And if the delta time or the return value don't fit at 8 bits, then we'll split it into 2 events, a call event and a return event. Okay, that happens less than 10% of the time. So over 90% of all of the events are call return pairs. So that's the entire format. The patches are pretty straightforward. I've patched 8 different files in the kernel. This is under Ubuntu 16.04, the 4.4 kernel. Here's an example patch in appic.c. There's just a couple lines that I added by hand that says, this is an earlier name DC for data center lab tracing. Now it would be KUTracing. There's a global kernel Boolean compiled in that says tracing is on or off. And everything always starts by saying, is it off? Because it's off for months. But in the live, at least Google data centers, sometimes somebody cares about some problem and turns it on and looks at the data. So this is not something you leave on all the time because it would be nice. It's a waste if nobody's going to look at the results. So there's a Boolean that says it's on, and there's in the loadable module, you can flip that Boolean on and off. If it's on, then you call compiled in just 4 pointers to recording routines, just the address of the routine. And a parameter that says which event, and the 0 in this case is the lower argument value. Do you have a quick question?
Yeah, quick question, Mike. I'm just curious if you're aware of jump labels.
I'm aware of jump labels.
You are aware of jump labels?
Yes.
Do you use jump labels to implement this?
No. I'll show you the implementation on the next slide.
Okay.
They're just calls. And
well, the fact is that you get rid of the actual if statement.
The actual.
The jump label would be a no-op. So there's no compare to a variable. When you're tracing off, you want full no.
Anyway, we are jump labels to avoid the test for the Boolean.
Exactly,
The
right.
test for the Boolean takes 0 time because it's 100% predicted.
Yeah, but you
for
waste
the ones where
a
it's not.
branch prediction entry
That's true.
for that.
Yeah.
And that's why I'm saying jump labels is a no-op, which does nothing. And it's actually all you just do a static key entry.
The entire path is 40 cycles. I'm not so interested in saving the one cycle.
But you're saving one cycle on something else too. So I'm just bring it up.
Out of 40 cycles, anyone in this room can save one cycle.
Yeah.
No one can save 12 cycles. Except for the people from Intel, they would actually build some of these 4 instructions that are highlighted a little faster. So this is a path that I want to insert one trace entry. There's a second check for is the tracing on because you really don't want to store anything in this trace buffer if it's not there anymore. There's taking the event number, shifting it over and orienting the argument, and inserting that. The insert reads the cycle counter, get cycles, compiles into RDTSC. There's get, a place to store this. Now, one of the complications is I'm tracing the beginning of a system call, and in the midst of this code, wham, an interrupt arrives, and the interrupt gets traced. Okay, and it's a preemptible kernel. The interrupt actually goes off somewhere else for a while, and it's a long time before I come back and finish the other half of the system call exit. So all this code has to protect against that without taking out locks very frequently, because that would slow things down. So I read the cycles, I call this routine to look at in a second that gets a place to store the 4-byte or 8-byte result. If it in fact is a place to store and not null, then take the argument and the time clock, shift it over and pack together and store it in out. And the find a place uses a per CPU variable because if you're tracing 24 cores, they need to be writing to separate cache lines, otherwise you're just hosed. You're always crashing the cache and you can't possibly be at 1% overhead. So each CPU core has to be writing to its own chunk of the trace buffer. So there are per CPU variables that simply say, here's the next place to write for this CPU core and here's the limit. So I have to pick those up and atomically read them because an interrupt routine might arrive in here. Let me finish this section, I'll get to your question. And then there's some comparisons to make sure we're within the limit, and then there's an atomic add that says allocate this space, no one else gets to use it. And then at the end, there's putting the CPU variable back, which also allows preemption. You had a question?
Yes. Are you aware of the local atomic operations? Because that could save you more than 12 cycles, much, much more.
The local atomic?
So given that you're working on per CPU variables, as you do get CPU var and put CPU var, this disables preemption for
Yes.
that code path.
Yeah.
So there you are working on per CPU data.
Yeah.
So basically, let's say XED64. Atomic 64 at return has lock prefixes. You don't need that. So there's the local.h header. So you can have the atomic effect on a single CPU.
So after I prevent preemption, you're saying I don't need the lock prefix on the atomic add.
Yep.
I am, however, still exposed to an interrupt getting delivered in the middle of this no preemption code.
The local atomic operations use atomic operations, but without the lock prefix.
Okay.
So from a single CPU perspective, you are executing atomic.
So that may speed this up a bit. Maybe you can get 12 cycles out of it. Well, what is 40 cycles? And then the trace buffer is allocated in blocks of like 64K, and at the end of every block, there's actually the path not shown takes out a spin lock within this code and allocates a new block and returns. But the overhead of that is down by a factor of 8,000, so it doesn't matter. So this is measured performance. So the actual, my goal was 1%, the actual is 0.25% overhead. 12.5 nanoseconds per event. So 25 nanoseconds for a system call return pair. And the space is also about 0.25%. So at that point, I don't have to worry about distortion of what's going on to the live load. It's a wonderful thing not to have to worry about. I also don't have to worry about, oh, I need to subset because it's too slow. I get to see everything. So just to summarize, it's a loadable module reserves in RAM. There's some patches in 8 routines. There's a total of 250 lines of source in the kernel, a large chunk of which are declarations of the global. And then there's a control interface to start, stop, and copy the trace off the disk, and then there's post-processing. So I'm going to talk for a bit about the post-processing. Yes?
Is your tracing fastpath all inlined within the caller site at every caller site, or do you have calls?
Are the calls inlined? No.
Because the 12 nanoseconds, I doubt it.
This is the performance with the code that I showed you. The calls are not in line.
Because just a call itself has something like 5 and more nanosecond overhead. If you're adding an atomic at return, I mean, you cannot do all that in 12.
All I can tell you is I measured this on an Intel i3. I will show you the results of it. I will show you pieces of code that run for 90 nanoseconds, including the tracing overhead.
No, I mean, if it's something that's not the branch predictions, actually it does take place on calls as well. So yes, calls do have overhead, but if it's just a standard thing, the CPU does optimize calls in a way where it can, as it's coming down, it actually does all the prediction for calls as well and calls return. I talked about this with Intel a little bit, so that could have been why you don't see a call. Some calls, yes, you see. What matters how well the branch predictor works. So depending on how the CPU and how it's run, you could have almost no overhead, or you can have a huge overhead. So you might have been lucky. That's I guess that's a thing.
But I mean, the 5 nanosecond, that's for a predicted call. I mean, the work I've done on yours, I mean, that's
we should
like
discuss that later, and I'll go ahead and finish
Yes.
the presentation.
Yep.
So the post-processing, there's basically 2 pieces. There's a piece that reads the raw binary trace files, which are just these 8-byte entries packed together, and turns the transitions, user to kernel, kernel to user, turns them into durations. During this time, we're in this routine. During this time, we're in this user mode process ID routine thread. And during this time, we're in this page fault handler, etc. And as part of that expansion into durations, every CPU core is writing into its own block, and the blocks are allocated at trace time. So the CPU number is recorded once at the beginning of each block. This expansion propagates the CPU number through all of the resulting entries. It propagates, the only time we record the process ID is when it changes the context of it. So this propagates the process ID through everything. In an environment where there's lots of client-server transactions done with remote procedure calls, RPCs, or messages or something, it's tremendously useful to include the RPC ID saying this piece of code in this thread is currently working on this RPC. That's how you get to see which RPCs are slow and why. And then the output of that is a JSON file, which will just drop through the standard system sort by start time. And then the second part is a little HTML file that reads the JSON, and then you can pan and zoom around, which I'll show you in a few minutes. This is enough information to show all the threads that are processing one of our slow transactions. It shows all the interference from other threads. There is no other interference possible. There's nothing else happening on the machine that isn't in the trace. It also shows all of the wait time, where you're working on some transaction and then you go get a software lock and you don't get it and you block. And then you wait a long time. And often performance issues are around waiting for locks. They're not around sharing the CPU or the CPUs. What you get to see when a thread running a particular transaction starts up again is the thing that happened right before that is the thing it was waiting for. So if you're coming out of Futex because whoever had the lock just freed it and made it runnable, you get to see that. If you're waiting on a disk interrupt, you get to see that. If there are no disk interrupts during your wait, you weren't waiting for the disk. So you get to see all of the information about why the total time happened. And it's pretty easy to take these in timeline across multiple machines, even though there may be time offset for get time of day or whatever of a dozen milliseconds between 2 different servers. NTP I looked at does not work well in this environment. It does okay, but it doesn't get you to microseconds. So this is an example of some output of two servers, and the client machine down here and the server machine down there, and I timeline them. The client is sending a megabyte of data, and there's a whole mess down here of interrupts, Ethernet interrupts, as it sends that megabyte packet by packet. And there's a matching set of interrupts on the server receiving those. The server actually does something trivial with it, and then sends a result, which in this particular picture, the result message of one packet did not arrive for 40 milliseconds, even though it could have arrived back here. And the reason is Nagel's algorithm is still on by default. And if you send something less than a packet, the default compilable kernel waits 40 milliseconds before it sends that partial packet because it's hoping to get more stuff to put in that packet. This is a disaster in a data center. So this is a little example of some of the just text form of post-process transition entries. So I'll show you a bit more of this. So none of this is useful if you can't have humans look at it and make sense out of it. So it works a lot on the display also. The goal for the display is to turn all these timestamps into pictures of what went on for 30 to 120 seconds and be able to zoom in, to pan and zoom and look at specific things. So I make this JSON file and load it into some HTML using the D3.js library, which some of you may have used, which is wonderful. And then if you get more than about 25,000 different timestamps on the screen, it starts to get slow. So part of the post-processing has a trim function, so you can say, this is the only part I'm interested in looking at right now, and also granularity, so you can say, in spite of the fact that things are recorded at 20 nanosecond resolution, lump them into spans that are a millisecond long or whatever, 100 microseconds. And then you get sort of a crude overview of all 2 minutes. You get to see the overall pattern. You get to say, what in the world is that? And then reprocess just that part at full resolution, and then you can zoom in on it. Or you can load 100,000 spans into the browser and wait a little while as you zoom. So they both work. It's important to have human meaningful labels. So the beginning of every trace has the names of all the system calls, so you don't have to remember that one is right or whatever. And whenever there's a new process ID that shows up, the name of that process is picked out of the kernel command line 16 bytes and put into the trace. And that's enough that you can start making sense out of these instead of just, oh, it's lots of pretty boxes. There's also a facility for user code optionally to add some markers for the trace, so that if you're thinking about some function, you can say, I put a marker at the beginning of that function and see. But those markers only cost 12.5 nanoseconds each. They're not going to distort anything except for the null function. So here's an example output trace. I'll sort of walk you through it a bit. This is a 4 CPU machine. This is time going on the x-axis sideways. Across the screen, it's about 800 microseconds. CPU 0, 1, 2, and 3. The thin black lines show that that CPU is in the idle loop at that time. The tallest lines with multiple stripes are kernel mode execution. And the half-high stripes, 2 colors, are user mode execution. And the colors are a function of which system call, whatever it is, or which process ID. So this is Hello World run from my desktop machine to a remote server that's running the tracing. It starts with this Ethernet interrupt, bringing in the packet that says /hello world. And it ends with this Ethernet interrupt, which is the interrupt saying that the ACK packet was returned for the last output prompt. And there's 800 microseconds in between. I also chose, for the purpose of this talk, to add 2 markers to the trace, one at the very beginning of main for Hello World, and one at the very end of main. So all of main is insert a marker, F right, hello world to sysout, insert a marker, return 0. So there's all this stuff going on for our industry's traditional simple program. I'll parse it a little bit for you. This is the Ethernet interrupt. This is the SSH daemon thread running. So the interrupt gets the SSH daemon thread running. It wakes up a thread called kworker3, which wakes up bash, command line processor, which gets the command. First thing it does, this is, after all, Unix, it's all bidirectional. So the first thing the bash does is it echoes back out through kworker3 to SSH. It echoes that /hello world, it echoes the command. Bash then spends, there's 67 microseconds here in the clone system call, creating another copy of bash, which cranks up and gets to the point where it does an execv to transfer to the hello world image. That runs a little bit of migration worker thread, which then moves this whole thing, which is now the hello world program, to another CPU, and eventually way down here we get into the kernel. We do the write of 12 bytes of hello world that goes to the kernel worker thread, which goes back to SSHD, which actually says hello world space and the carriage return in the end. Meanwhile, this exits, goes back, wakes up the main bash, which then writes the $ prompt for the next command. Oh, sorry, well, thank you. So I'm going to point out a couple little details, and then I'll bring the HTML for this up live. Over at that edge, oh, I should mention, what are these little sine waves? There are people in this room who know what those are. And coming out of idle, there's this little sine wave, and then it executes some code.
Frequency
Your process?
frequency, yes.
You get to see everything here.
Frequency scaling.
Sorry?
Frequency scaling.
Frequency scaling. This is coming out of C6 power saving state. If you look really carefully here and here and a few more places in very light gray, is the M-wait instruction that says go into C6 power saving. This is coming out. This is 13.3 microseconds on this chip. It actually can be a lot of time. And it's one of these things that we're totally invisible to, we never think about. Back up to one of the other things. All these things here with the red tops, the light green tops are system calls, the light red are faults, and the light blues are interrupts. Page faults. Tons of page faults. Tons and tons of page faults before you ever get to the first line of the C code. Another thing that we never think about that's invisible to us, but when you see it, and you see that it's taking 20% of the time, you get to say, oh, that might be related to my performance problem. But if you can't see it, you would never guess. We were going to talk earlier that the time spent in page handling turned out to be a big deal. And with a tool like this, you could have seen it instantly. So I'm going to talk about this one edge where we go from hello world to the kernel worker thread to SSHD. And at that edge, you can see the page faults here. There's an fstat. After we get into hello world, there's 3 more runs through page fault. There's an fstat. There's a couple break calls to allocate the runtime stack. And then we finally get to the right. Here. Okay, so that gets the kernel worker thread going, which wakes up SSHD. Now, SSHD was sitting in the idle loop, on the CPU port was in the idle loop, but it doesn't take 13 microseconds to wake up. And the reason is, on this machine, CPUs 1 and 3 are 2 hyperthreads of the same physical core. When that core woke up back here to run the kworker thread, It's the same core that's going to execute SSHD, so there's no delay at this edge. If these were separate cores, then there'd be another 13 microseconds here. And here, now that we've expanded a bit, you can see where the M weight is for the next delay. So those are the kinds of things you can see. So I'm going to show you one more set of things you have not seen before, and then I'll do the quick demo and get done. So this is showing instructions per cycle in executing real code with 0.25%, actually 0.5% overhead, because reading the number of instructions required takes 35 cycles and adds to my 40-cycle budget. Each of these little triangles shows for each interval instructions per cycle in a very coarse way. 0.25% instruction per cycle, tilde a little, a half an instruction, tilde more, one instruction, and pointing straight up 2 or more instructions per cycle. So this is less than an instruction per 4 cycles or more. And what we get to see here, this is a sys-write of a megabyte that takes 184 microseconds. And the sys-write code is running at about half an instruction per cycle, except near the end it's running at less than a quarter. And then we wake up from that back to the program that was running, which is some user mode program, but we get to see it start up at half an instruction per cycle, then 1 instruction per cycle, and then 2 instructions per cycle, and then stays at 2 instructions per cycle. I've never seen that edge before. Probably we're taking lots of cache misses after we come back from the operating system. Well, yeah, now you can see them. They're not as big a deal as I thought they were. Here's another example. This is in front of that same write. There's a series of page faults. This is the page fault routine execution rate, instructions per cycle. This is the user mode code that's getting interrupted. We're generating faults. So here's the page fault running at less than a fourth of an instruction per cycle. Then it's at 1, then it's at a half, and then it's at 1, 1, 1, 1, 1. If you have a whole burst of system calls, they get faster during the burst. So, system code is always 100% cache misses, I don't have to worry about it, is also false when you get to see the fine detail. Unless, of course, you're running page faults on 2 different cores and they're taking out spin locks and things and slowing each other down. So here's an example of one thread wakes up another thread. This is sending the IPI interrupt to the other processor saying, go look at your scheduler queues, there might be something for you. This is the 1.82 microseconds later interrupt delivered. The rest of that time is through the 8-bit hardware. Interrupt delivered runs the scheduler after a little bit. The scheduler, in the middle of the scheduler, it runs the RCU, read, copy, update. Wonderful thing to delay free system memory resources. It runs here. And then you get back to the scheduler, and then it finally goes to the new program that this guy tried to wake up. So you get to see all those details. And sometimes there's big delays in that path, and that's what you're looking for. But if you can't see the path, you can't find the delays. This is the last of these. This is in green over blue, a program that all it's doing is it's sweeping through 4 megabytes on chips where the last level cache is 3 megabytes. So it's doing the worst case, but linear sweep, cache, everything misses to RAM. On the second core, there's another version of the same process, another PID number with different colors, blue over green, doing the same thing. You can see from the gaps, this is a marker that I inserted in the source code at the end of each pass. You can see first that the passes are running on the order of 2 microseconds, 2 milliseconds each, and they're both sort of slow. If I stop that process, or in particular, the Linux scheduler stops it and runs this other process, which is only going through 30K bytes and is hitting 100% in the L1 cache, except at the startup that I haven't expanded, then this guy gets twice as fast because nothing's interfering with it going to big memory anymore. So You get to see that level of interference. Some other thread making my cache accesses slow. But you have all in this room hand wave might be happening, you get to actually see it.
A real question, just, I'll ask a question, you can repeat the question. Just how do you record cache misses?
I don't, I just record the time. If the cache misses don't slow it down, I don't care.
So you don't know, so you're just assuming that it's the cache, you're just basically, you're looking at the time.
These are little loops that I built, and that's the only thing that's going on is changing from this to that. And the source code for this is 3 lines of code, and the source code for that is the same 3 lines of code with a smaller number. There is nothing else happening on this machine. There's no hidden stuff.
Right. So what my point is, I'm saying is that you're just assumptions or knowing of the CPU properties that's cache misses that's causing the delay.
I know what the 3 threads there are doing.
Right. So it's
And
not,
the only possible source of interference, there are no interrupts or anything. The only possible source of interference is shared CPU problems or shared memory problems.
right.
These are on different CPU threads. These are really separate cores. So the only remaining possibility is memory interference.
Right. So it works if you have like basically a simple program and you know what it's doing, but when you have more complex programs where you don't, it's harder to see how memory is being
When you
shared
have more
between
complex
these.
programs, the instructions per cycle can give you strong clues about what can and cannot be going on, but there's more to investigate. This is not usually the biggest problem, but if you think you've got cache crashing problems, this can reveal them.
Yeah, but then you probably need something to read the cache misses and such.
You could. Then you're getting somewhat processor specific, and you're getting much slower to get into the kernel and read these things. This is just one instruction from that Intel is more or less optimized, so it's only like 35 cycles instead of 70.
So how do you record the IPC?
Everywhere, at every transition, I read the cycle counter and I read the instructions retired counter. That's it. How would you record IPC? The minimum work you can do is read those 2 counters. And so let me just switch for a second. I'm going to put a late on time. This is the output of the world. This is just about the script and my JSON. You can roll around and go look at whatever's happening and pick off. Here's a page fault that took 350 nanoseconds. Here's M map. Of course, loading the program does an M map of the program image and then eventually M maps it and stuff. So you can see all these pieces with the hello itself. This is the fstat, seeing if sysout actually exists before writing to it down here. And when you can do this and do little time sections, say from here to there was 41.8 microseconds. You can track down pretty quickly when you see a big blob of time that you don't understand. You can track down what's going on in that blob of time, and if it's relevant to your performance problem, fix it. So let me get out of this and do the last few slides. Shrink. All right. So a little bit of comparisons. Many of you worked on the things that are here. I did find that A trace, B trace, C trace, all the way through Z trace. All of them. That's why I chose 2 letters instead of 1 for KUTrace. And a lot of them are very flexible, but of course have a lot of overhead on this particular area. So here's a bunch of traces. This is the things I care about columns. Does it show you all programs or just one program? Does it show you all the system calls? Does it show you all the interrupts and traps? Does it use interpreters and scripts and ASCII output like strace does, in which case it's much too slow? How long does it actually take timing it to do when you get UIDs in a loop after subtracting the loop overhead to see how long it takes? And the time overhead for the ones that are reasonable. The free and green are the ones that can show you everything and don't have to go through an interpreter. And even with those, I'm 8 to 16 times faster and much less space overhead. And remember, the space overhead turns into time overhead because of taking more and more cache misses with bigger entries. So just to summarize, I will leave this for you all to read when you look at the slides, but I give credit to Ross Perot, who came up with most of the early implementation at Google. So I think there's a need in data centers for something with this low an amount of overhead and a big enough purview to see all of the interference, not just guessing at what might be happening. It turns out, I didn't know when I started, the kernel user cut point of what to record is a good cut point. It shows everything is happening. It's enough information to reconstruct what every CPU core is doing every nanosecond. And other than that, it's not a huge amount of data. Took a lot of careful engineering to hit this sort of speed. There's just a little bit of extra information added to get names in. And that doesn't take much time because it's once per name. And having a good display mechanism makes it useful to real people to sort out what's going on. You can't do this from a million lines of numbers. So we stop there and take some questions. I've got 3 pages of references on a whole bunch of traces and some of the Google surrounding context for data centers.
Questions?
Hello. Did you run any tests to validate that the real overhead is less than 1% of CPU time?
Yeah. I did a million system calls with and without tracing, and one was 60 nanoseconds per entry, and one was 85. And I subtracted and said it's 25 nanoseconds per entry, per pair of entries. Enter the syscall and exit the syscall. So that's the best case. Any of this stuff, of course, can be slower if it doesn't happen very often, and you aren't in the cache when you go to the tracing code or whatever. But if it doesn't happen very often, it can't slow you down very much. It only slows you down when it's happening all the time, at 200,000 events per second, and when that's happening, then you get the good case. Question back there.
Yeah, so when you did the tests with tracing and without tracing, without tracing, you didn't add patches or anything. You just ran it before I did any modifications.
No, I ran it with the tracing turned off, but the
but
the Boolean tests of am I tracing are all there.
right. What I'm saying is I would just see if there's a difference if you just remove all the patches and see
I
how.
understand what
Yes.
you're asking.
Yes.
I actually did that early on, and there was no discernible difference, but the run-to-run variation is tiny.
Right. So I just get curious. So whenever I do my thing, I always removed.
It appeared to be well under a nanosecond.
Okay. Yep.
Yeah. No, okay.
So, well, looks like this tool could be quite powerful.
Hang on just a second. A partial answer to your question is, this sort of thing with the tracing turned off is running on all machines in Google data centers today.
Yeah.
It's that low enough overhead for the testing of is it on.
I know.
All right, go ahead.
So you have some sweet spot in terms of performance performance overhead and management information. And do you have any real life examples? Because well, the examples you've shown are quite simple in terms of you basically showed that you can observe the things we already know in terms of page flows, cache usage, and stuff.
So the question is, do I have other examples?
Yeah. More like
So I have a bunch of examples. I didn't put them in this slide from Google of finding real bugs in search and in Gmail. And Gmail front end is written in Java, and the back end is written in C++. And the same machines are also running a disk server, and they're also running web servers, and they're running batch programs, and the batch programs are banging the caches sometimes and making the user-facing stuff too slow. It's all there.
yeah, because that's what could be interesting because well,
Yeah, so I have a whole different talk on examples of bugs found in this. I wanted to either tracing summit to talk about the tracing mechanism. So maybe we can take one more question and then you can.
One question that I have. So if you go back,
Here is the way.
Maybe I can ask up one.
so if you go back to the benchmark slide,
I have a benchmark.
so you will see that both ftrace and LTTNG
Yeah.
are in the area of 500 nanosecond. But the thing is here, you are actually, so both of those tracers, the way they instrument the syscall entry and exit, they actually go to the PTrace slow path in entry.s, which is a huge part of that number.
I don't have any complaint about that.
So I'm just curious about how do you hook into the syscall entry and exit? How do you instrument them? That I'm really curious about that.
In the assembly language for x86 entry.c, I added the same trace call I showed you in APIC.c, not entry.c, entry.s. I added the call to do the trace right after saving 11 registers. And I added the call to trace the exit right before restoring the 11 registers in this incredibly messy code that has 3 different ways of getting in and 3 different ways of getting out and lots of circumstances of test whether I preempted a call in the scheduler, and all of the system calls that don't go through the standard exit show up when I trace the scheduler, which is how all the other ones get out as far as I know.
One point I have is we've been waiting for Andy Lutomersky to get his modifications in, so we could speed out each tracers by hooking onto syscalls.
Google actually tried to submit this upstream in the first version around 2008, and it was rejected because it was solving a problem that the Linux community did not think it had.
Yeah, I'd like to have that fixed, really.
This, the question over there.
Yeah, question.
I have a question. So you show us this beautiful event display, which is very good for looking into a particular problem. But have you tried to, like, kind of statistical, look into this data, for example, trying to apply a principal component analysis?
No, every actual performance bug I found at Google was unique. I didn't find any magic, oh, we'll have an AI system go find all the bugs. I didn't find any statistics that were useful. It's go for this instance and see why that particular user-facing transaction was slow. And once you understand the dynamics of why they're slow, you know, somebody else has the lock or whatever, once you understand the dynamics, the fixes always turned out to be easy. But I never found a magic statistical way of finding the problems in the first place. So let's stop there. Happy to ask.
One more question from me. So one of the major difference I've seen with your approach is that so you are really selecting a tiny subset of the payload, right? A single parameter, really compact, small representation. So if you look at the existing kernel tracers, I mean, we do have tiny headers as well. I mean, 32-bit. I mean, we do a lot of effort to minimize the amount of space consumption. So it's not bloated per se. However, I mean, for system calls, we do gather all the parameters. So one question is, would it be, if the speed is comparable with the existing tracers, if you have the ability to select, to say, oh, I only want to record a single field and not the whole payload, so to have some flexibility there, would it?
If somebody else built a 12.5 nanosecond tracer, there is no need for me to do that. We couldn't find one.
Okay, thank you.
Okay, if you have a whole lot of choices and you're spending a whole lot of if statements saying, is it this choice, is it this choice, is it this choice, you can't be this fast.
No, the idea is to template
You were the
the
one just
functions.
beating me up for testing whether I'm tracing at all. All right, thanks.
Thank you.